So let's step back and take a look at the Keeling curve in a broader perspective. Dave Keeling started measuring atmospheric CO2 in 1957. It was about 315 parts per million, and it's now about 400 parts per million. But what about longer timescales? What was it doing in the 1920s? What was it doing in the 19th century, or even before? How much did it vary over this timescale? To get at that information, we have to look at other sources, because obviously we don't have bottles of trapped gas available. But there is actually one source where we can get trapped gas from the atmosphere, and that's from ice cores. Glaciologists learned a long time ago that they could drill cores through the snow and through the ice and actually sample the air trapped in the ice bubbles. Now, just in snow itself, snow is full of air, and glaciologists learned how they could actually dig deep pits in the snow and then sample the air trapped in the snow laterally and reconstruct the atmospheric composition back over the last few hundred years. And so you can go to various places in the world, to Greenland and to Antarctica, and actually reconstruct the carbon dioxide levels back over the last millennium or so. And what you see is a very smooth curve. The diffusion of air in the pore spaces of the snow doesn't allow you to see a lot of variation, but you see a pretty smooth change from the industrial levels, around 350 parts per million, going back to around 280 parts per million in the pre-industrial level. And from about 1800 back to about 1000 AD, you see fluctuations around 280 parts per million. And that's what we call the pre-industrial level. But if you go deeper in the snow, what happens is the snow gets compacted more and more and eventually turns to ice, and the ice eventually seals off so that the pore spaces where the air was diffusing slowly in and out of this column of snow ultimately get trapped as bubbles in the ice. So we can drill cores deep in the ice and take the ice and bring it into the laboratory, put it in a vacuum chamber, and then melt the ice and release the gas from those bubbles, or crush the ice and actually release the bubbles mechanically and measure the air in those bubbles and actually measure the isotopic composition of the nitrogen and of the oxygen and all of the other components, and measure the carbon dioxide concentration. Some of the first work was done in Greenland. There were two great scientists who pioneered this work. One was Willy Dansgaard, and the other was Hans Oeschger. And they were responsible for the big Greenland drilling program, of course, all over Greenland on the ice sheet there, and that have told us a lot about the evolution of atmospheric CO2 over the last 100,000 years. It turns out that Greenland, though, is relatively warm. Remember, Greenland's not on the pole. Greenland is actually fairly far south. It's only at about 70 degrees north or so. And so because it's warmer, it actually has more moisture in the air and it snows more. And so the ice accumulates faster, but that also means that it doesn't go back as far because it's constantly building up snow, and therefore the old snow is getting compacted and pushed out to the side. So the records from Greenland only go back about 100,000 years or so. There's some advantages of those records because they're laminated. You often see seasonal banding, and that allows you to count the bands and know exactly how old they are, but you can't go back very far. But it's very different in Antarctica, and as Willy Dansgaard and Hans Oeschger were working on Greenland, the Russians were actually drilling ice cores in Antarctica, and the program really took off when the French started to collaborate with them. Pioneered by a number of French scientists, including Jean Jouzel, they drilled a number of very deep holes, including one at Vostok. Now, Vostok is not in the very middle of Antarctica, but it's in East Antarctica, and it's in one of the coldest places in Antarctica. The temperature is about minus 90 degrees there in the wintertime. It's extremely cold and very, very dry. And what that means is it snows, but very, very little. It's so cold that the air doesn't hold much moisture, and so the precipitation is very, very small. Now, that's very bad if you want a very high-resolution climate record, but it's very, very good if you want a very old climate record. So the ice cores drilled down near Vostok records some of the oldest ice that's been recovered. More recent expeditions near Vostok, the Epica core, for example, have gone even further back. The Vostok ice core went about 400,000 years back before present, and the Epica core extended that to about 650,000 years. And now we have ice cores that have gone all the way 800,000 years back before present. When you look at the carbon dioxide records from Vostok and Epica, and these old ice cores from Antarctica, what you actually see really puts the Keeling curve in perspective. First of all, the first thing you notice is that there's an enormous amount of fluctuations, but they seem to be somewhat regular. Periodically, you get minima in CO2 concentration around 180 parts per million. There's a lot of fluctuations, but you never really go much below about 180 parts per million. And on the high side, the maxima occur at around 280 parts per million, a couple of times maybe reaching almost as high as 300 parts per million, but never really going above 300 parts per million, at least over the last 800,000 years. The fluctuations have a lot of structure, and sometimes it looks like CO2 changes occur relatively fast. That's partly an artifact of looking at it on this sort of graph where you're showing 800,000 years of geologic time. In fact, if you look at one of the fast changes, like the change 20,000 years ago between the minima around 180 parts per million and the maxima, the 280 parts per million that we think of as the pre-industrial level, actually that change occurred over 10,000 years. It looks very fast in this time scale, but in fact it occurred much more slowly. Now, to put that in context, the Industrial Revolution, burning all of the fossil fuel over the last 150 years or so, has taken the pre-industrial level of 280 parts per million and raised it up to about 400 parts per million. But instead of over 10,000 years, that's occurred over about 100 years or 150 years. So it's occurred roughly 100 times faster. So in some ways, this is really about rate. The rate of change of carbon dioxide is just so much faster than anything the Earth has experienced for a very, very long time. The other important point is that the carbon dioxide levels never, over the timescale that we have ice core records, never went above 300 parts per million. Now, today we're not only well above 300, we're at 400 parts per million and heading towards 500 or 600 well before this century is over. Now, this is a geological experiment that hasn't been done for a much longer period of time, and later on we'll talk about some examples in the geologic past when those sorts of carbon dioxide concentrations did exist, and of course the Earth was a lot warmer. When we look at these fluctuations over the last 800,000 years, this is a time period we call the Pleistocene, these carbon dioxide fluctuations are associated with large changes in climate. So 20,000 years ago, when carbon dioxide was 180 parts per million, this was what we call the last glacial maximum. And the world looked quite different than it does today. There was a huge ice sheet over most of North America. The ice sheet extended down to New York City. Here in Cambridge, Massachusetts, we'd be under about 1 kilometer of ice. There was a big ice sheet over parts of northern Europe, and of course there was more ice on Antarctica as well. Overall, there was so much ice on continents that sea level dropped about 130 meters, or about 400 feet lower, because of all the water that was stored on the continents. It was a very different world. Global average temperature was about 5 degrees colder. And during the pre-industrial period, that is the world that we were used to before we started burning all of this fossil fuel. CO2 was 280 parts per million. And in fact, you see this going back through time, these fluctuations between glacial maxima and glacial minima. We call the glacial minima interglacials. So the glacial maxima are what we think of as the ice ages, and then the glacial minima, those are the interglacials. They're really not interglacials. You can think of that we're actually still in a glacial world. There's ice on Antarctica, there's ice in Greenland. This was, of course, not true 50 million years ago. We'll talk about that later, but during the Eocene, a period between about 34 and about 55 million years ago, there was no ice anywhere. No ice on Antarctica, no ice on Greenland. It was a very different world. But at least for the Pleistocene, we're in a glacial world. It's just fluctuating between these extremes, and the carbon dioxide is at least one important part of those fluctuations. What we're going to do today is look a little more deeply at the causes of these Pleistocene ice age cycles. We're going to try to understand what the mechanisms are that are responsible for these huge climate swings and see what kind of lessons we can learn for the situation we're in today. This image shows a picture of what the northern hemisphere looked like 18,000 years ago during the last glacial maximum. You can see that the ice sheets covered most of North America, all of Canada, all the way down through the middle of the U.S., reaching all the way to New York City on the East Coast and well into California on the West Coast. You can see a smaller ice sheet over Northern Europe. We call it the Fennoscandian ice sheet. You can also see that there was really no ice in very cold regions today, like Siberia. If you compare what the world looked like 18,000 years ago to today, it's quite remarkable what a big change this was. The difference between the world on the left and the world on the right in global average temperature is about 5 degrees Celsius. This is surprising to some people. We don't normally think about global average temperature. We experience changes of 20 degrees or more on a single day between night and day. Day-to-day variability can easily be 20 or 30 degrees. So a change of 5 degrees seems pretty small, but in fact, it's the difference between ice sheets covering half of North America versus essentially no ice anywhere in the northern hemisphere except for an ice sheet over Greenland and the Arctic Ocean being covered with sea ice. One of the most important reasons the world was so much colder 18,000 years ago was the ice sheets themselves. The ice sheets, as we've talked about, affect the Earth's albedo, how much sunlight is reflected back to space. So there's a positive feedback here where if you have more ice covering both the ocean and the land, you reflect more sunlight and the Earth gets colder. And we think that the ice itself is responsible for about half of the cooling that we observe. That is about 2.5 to 3 degrees out of the 5 degree total cooling during the last glacial maximum. We think much of the rest of the temperature change was due to carbon dioxide. Now, what was driving these changes? A hypothesis that really goes back to the 19th century is the idea that subtle changes in the Earth's orbit around the sun affected the climate and ultimately drove the ice ages. These cycles are often called Milankovitch cycles, after the famous scientist from the 1930s, Milankovitch, who did some of the most important work calculating these cycles and trying to understand how they might affect the ice sheets over time. The 3 basic cycles that we think about are, first, the eccentricity of the Earth's orbit. This essentially means how elliptical the Earth's orbit is. As you know, the Earth rotates around the sun, and it's not a perfect circle. It's actually an ellipse. Now, it turns out that if you look carefully, it looks a lot like a circle because it's close to a circle, but it's actually just a little bit longer on one end than the other. And that amount of ellipticity changes very slightly on a time scale of 100,000 years. Becomes a little bit more elliptical or a little bit more circular. A more important parameter is the obliquity cycle, which has a period of 41,000 years. This is a subtle change in the tilt of the Earth's axis. Currently, the Earth is tilted by about 23.5 degrees relative to its orbit around the sun, and this is what gives rise to the seasons. At some times of the year, the northern hemisphere is pointed towards the sun, and that's when we have summer in the northern hemisphere. And then at other times, it's pointed away from the sun so that we have wintertime. If the Earth is more tilted, if it increases by a few degrees, that will strengthen the seasons, and so you'll have warmer summers and colder winters. On the other hand, if the obliquity is a little bit less, you'll have slightly warmer winters and colder summers. The seasonality will decrease a little bit. These 2 cycles, eccentricity and obliquity, interact to create what we call the precession of the equinoxes, which has a period around 20,000 years, actually a couple of different periods, one at 19 and one at 23,000 years. The precession of the equinoxes really comes from the interaction between the tilt of the Earth and its eccentricity. Because it's an ellipse, at one time of the year, the Earth is closest to the sun, and 6 months later, it's farthest from the sun. Currently, the Earth is closest to the sun during the winter time in the northern hemisphere. So the Earth is pointing away from the sun when it's actually closest to the sun In the summertime, when the Earth is actually pointing towards the sun in the northern hemisphere, it's actually at the far end of the ellipse, so it's actually farthest from the sun. A lot of people think that we have summertime because the Earth is closer to the sun, and it's actually just the opposite. During the northern hemisphere summer, the Earth is actually farthest from the sun. The opposite, of course, is true for the southern hemisphere. Where the Earth is in its axis relative to its northern hemisphere summer and winter actually varies. And that's what we call the precession of the equinoxes. So every 20,000 years it comes back to the same place. But 10,000 years ago, the situation was reversed. So we would have slightly warmer peak summer because summertime in the northern hemisphere would be closest to the sun, and wintertime in the northern hemisphere would be slightly colder at its peak because it would be furthest from the sun. So all of these three cycles interact to give rise to the ice age cycles that we observe in the geologic record. Now, one thing that's very important to understand is that the obliquity and precession of the equinoxes, the two largest factors in affecting the Earth's radiation, they don't actually change the amount of solar radiation the Earth receives. All they do is distribute it differently over different latitudes and over different times. So, for example, if the Earth is a higher obliquity, is more tilted on its axis, it doesn't change the amount of sunlight the Earth receives. All it does is it changes where that sunlight is distributed from the north to the south. Similarly, the precession of the equinoxes doesn't actually change the amount of sunlight the Earth receives. It just changes the strength of the peak summer versus the strength of the peak winter. So in fact, it's kind of remarkable that these relatively subtle changes in the Earth's radiation give rise to these enormous changes in climate.